Number 2, SAT verbal scores are normally distributed with a mean of 430, standard deviation of 120. If one student is randomly selected, find the probability that he or she obtained a score less than 360. And then the following questions, all these questions grouped together should look quite familiar. It's one of your quizzes where I asked you to use a normal distribution. And two methods of doing this. One is using the table and finding values from the table. But I actually don't prefer that because it's a little cumbersome. Although you will have a table on a test, I prefer that you actually use a calculator for this because it gives us a slightly more precise measurement or precise probability. So for all these things, we'll need a normal distribution, and so let's see. I got my normal distribution drawn here. It's good practice to try to draw the normal distribution as you're doing these things. So let's do problem number A. And we'll need 4 of these, I assume. And so let's just make some copies up there already and use them as we go along. So problem number A, one student randomly selected, find the probability that he or she obtains a score less than 360. So the only important thing here in terms of drawing is knowing if 360 is to the left or to the right of the mean. The mean is 430. So 360 would be to the left of that. And we want the probability that a score is less than 360. So you would shade in the left side over here. By doing this visual, it'll make your notation look a little bit easier to write up. It's less than 360, so I'll have x is less than 360. 360. And then, like I said, at this point you can go into the you can find the z-score and then go to the normal distribution table, table A2, and then find the value. But like I said, I prefer if you actually use a calculator. So just by the way, we're looking at this thing, you're shading everything to the left of this. So according to the calculator, you want your normal CDF function to take in the low value of minus infinity, and our notation for minus infinity in the calculator is 1e to the 99, and this is symbolically speaking, it's like minus infinity. And although, the scores don't technically go to minus infinity, you can actually take this from 0. But since they don't go from minus infinity, I mean, theoretically, we should be looking at this as if it was coming from minus infinity. But you can put 0 here, and the values would be a little bit different, but close enough. But if you write it down, as I check it, it'll be clear to me what you did. So the high value, so the input for normal CDF is low, high, mean, and standard deviation. So the low is minus infinity, the high is 360. The mean is 430, and these things, the mean and standard deviation, should be given in these problems. Standard deviation is 120. And so, let's see, for the sake of making space here, I'm going to put this down below and go to my calculator and then punch in those values. So the normal CDF, second, distributions. The first one's normal PDF, which we will never use. You can read about it if you want to know how it's used, but we're going to use normal CDF. And the minus sign is this minus sign next to the enter button. 1 E is above the comma, so second function in the comma. 99. By the way, this is 1 with 99 zeros. Comma, the high is 360. Comma, 430 for the mean and 120 for the standard deviation. And let's press enter. That's 0.2798. 0.2798. By the way, just to clarify something, when you're looking for probabilities, probability value are always quantities or values that's between 0 and 1, so that's just another way to check to make sure you're getting the correct answer, correct result. Let's take our second graph over here and let's get ready to do the next problem, part B. If one student is randomly selected, find the probability to obtain score greater than 440. So again, the mean is 430. So now, this time, 440 is off to the right. And we're looking at values greater than 440. So this is going to involve using positive infinity. If you had values between two things, then you would just, the low would be the low value, the high would be the high value. But in these two examples, we're looking at probabilities that are either less than or greater than, and so they're going to involve those high numbers, infinity. So probability that x is bigger than 440 would be the normal CDF. I look for this in the exam just so I see what you're inputting into the calculator. So in case you get it wrong, I would know which formula you use. I can still give you partial credit. So the low is 440 this time. The high is infinity. So that's 1e to 99. And the mean, 430. Standard deviation is 120. I'm out of space here, so just going to squeeze those numbers in like that. And when you're doing your calculator work and you have a set of problems that have the same mean and standard deviation, you can press second and enter. They'll give you the last entry in your calculator, and then you can either overwrite it or you can delete some parts and insert things. So the insert is second function of del. So I'm going to insert the 440 here and then put a comma, and then I have 1e to the 99, so I don't need my old 360 that used to be there. The mean is standard deviation, and so that's my value. I'm going to copy this and send it to our notes so that we have a copy of actually the two values that we just computed. This is 0.4667 or 668. Usually with probabilities, I'd like to have the probabilities rounded off to 4 decimal places. That's a good size. For part C, there's two types of problems. One is a problem where you find probability. Another one is a problem where you find your actual value, so your z or your x value. Okay, well, actually, it doesn't ask that question. Let's do part C. 100 students are randomly selected. Find the probability that their mean score is greater than 440. So this is different from the previous problem because you're not looking at one student being randomly selected. You're looking at 100 students being randomly selected. So this actually involves the central limit theorem. So with that central limit theorem, what we have is more or less the same setup. Get the mean 430 and 440. So from 440 to infinity. But the big difference here is because this is taking a look at 100 students that are being randomly selected, and then you're finding their mean score is greater than 440. You set up your notation not by using x, but by using x bar bigger than 440. And this is going to use the same command, but there's going to be one slight difference. You got 440, 1, e to the 99, 430, and this is where the difference comes in. The standard deviation is no longer the same standard deviation, but rather it's the original standard deviation divided by the square root of 100, or divided by 10. And so our setup in our calculator, again, I'll press second and enter, and it's exactly the same setup, except I'm going to put divided by here, square root of 100, or I suppose you could have just put 10. So this is what we were looking at. Oops, that didn't go well. Let's try it again. Let's get our calculator. Screenshot and take it to our notes. So your result here is 0.2023. And let's see, part D. Suppose a research Acme prep program, and you find that 100 of their students achieve a mean of 440. Does this seem reasonable to conclude as an effective program to enroll in? Well, theoretically, let's see if we can write this in words. Oops. So theoretically, there is a 20% chance that any random 100 students can achieve a score of 440 or higher. So if you think that that is a small probability, then this might be something special that this particular group has. So what you want is a small probability that would represent the the uniqueness or the specialness, I guess, to describe that. So 20% isn't quite small. I mean, small, we're looking at kind of like 10%, maybe even 5%. So like as in the significance levels. So I'd say it doesn't seem like it's out of the ordinary. This is out of the ordinary. So not so effective, I would conclude. For some people, it might be effective, and I would just need a fairly good justification. And as long as you can explain why you thought it was good. Okay, this is problem number 2.